Welcome dear students. So today we'll be taking up the Michael reaction. The Michael reaction is a very simple, interesting and at the same time useful reaction to create carbon-carbon bonds. It converts activated methylene compound and a conjugated carbonyl to the corresponding addition product by using a base as a catalyst, followed by acid workup. Or we can also say that it's the addition of a carbene ion to an alpha-beta unsaturated carbonyl compound. One of the most useful method for the mild formation of carbon-carbon bonds. It is used to synthesize all kinds of natural products and drugs. This method has high efficiency, simplicity, and is a green approach. These are the goals that are actually pursued by organic chemists. They look to these goals, these aims to be fulfilled, and so Michael addition fulfills them duly and therefore is an important reaction. Now we'll see as to how this reaction proceeds. What are the reactants? As I mentioned earlier, here we have shown this is the Michael donor. Now EWG, just in short, this is the electron withdrawing. So electron withdrawing groups, they facilitate because they make this hydrogen at the alpha position acidic so that its carbon-hydrogen bond is weakened and it can easily leave in the form of an H positive in the presence of a base. So this, once it leaves, it will be a carbene ion here, carbon negative, that means a Michael donor. This is an unsaturated Michael acceptor, electron withdrawing group. Many a times it is carbonyl, though variations have now been put up. There are different synthetic methods using other variants as long as the electron group, this electron withdrawing group is present here in the, so that alpha beta unsaturation is present to the alpha position. So this, by virtue of the movement of electrons, this electron pair towards the electron withdrawing group will be a positively charged and the beta carbon. So it will be a Michael acceptor. All this takes place in the presence of a base to give us the product. So this is basically the Michael addition in its simplistic form. Let's see what can be the Michael donors. I have written a few Michael donors over here. These are the Michael donors. Michael donors means implying that they will be able to produce a carbene ion which is well stabilized. That is, in other words, stable enolates, because that's necessary. So 1, 2, 3, 1,3-dicarbonyl this is. And once, see, in between this methylene group has 2 electron withdrawing. That is why active methylene. So this will give an H positive. Hence the carbene ion will be stabilized. Carbon negative will move here. This will move here. So this is stabilized by this. On the other hand, this can move here. This can shift here. This is stabilized. So it's very well stabilized carbene ion. Hence it won't be a very strong one. So this reacts, all these now, as I've shown here, these will be reacting with the Michael acceptor. This too, again, here it is, this ethoxy group is attached, methoxy, C2H5, CH3, CH2O, CO. This is just 1,3-dicarbonyl. Now this is again, we can see the active methylene, this time the electron withdrawing group on either end. This is C2H5, CO, C2H5 and the ester that is, and here it is NO2, nitro, again electron withdrawing. Here active methylene in the next example, and the active methylene is again surrounded by, on either side, by these electron withdrawing groups, which also stabilize the carbene ion at the same time by resonance. Similarly, this active methylene here with 2 electron withdrawing groups. These are all the Michael donors. Michael donors means they can form carbene ions. Now this is the Michael acceptor. The Michael acceptors, as is seen here, are alpha beta unsaturated compounds attached to electron withdrawing groups. The electron withdrawing group can be a carbonyl or it can be any other. So here it is the CN, which is nitrogen and carbon triple bond. So these pi bonds will be pulled towards nitrogen, and this carbon in turn will become positive, and it will attract this electron pair towards itself, so that this becomes positively charged. That is a Michael acceptor, to accept the electrons. Now again, this is a Michael acceptor, because this will draw the electron towards itself. So this double bond will move here and this carbon will become positively charged this end. Similarly, the ester COR, this again is a Michael acceptor. So Michael acceptor basically alpha beta unsaturated, which are attached to an electron withdrawing group. Seeing to how where we can apply Michael reactions, their importance. So if we have this type of a reaction here, this type of a reaction, what is it showing, this type of a reaction? See, you're well familiar with this, a carbonyl compound. A carbonyl compound, when it is reacting carbon positive, so nucleophilic addition, so this is 1, 2, because we are discussing carbonyl even with the Michael acceptors. So see here, this is 1, 2. 1, 2 means that carbon here will be accepting the electrons. So because it will be positively charged by virtue of this shift of electrons, electromagnetic shift. So R negative, and this is a strong nucleophile. Grignard reagents, organometallic reagents for that matter, they are very strong nucleophiles, or good bases, strong bases. So what will they do? Because they are strong bases. Therefore, in these cases, when they react with carbonyl compounds, they will give the 1,2 addition. As you can see, we've studied them earlier, very common reaction. The 1,2, they'll quickly attack this carbon positive, R negative, and hence we will get this product. This is the 1,2 addition. 1,2 addition. Now let's see what happens when we do not have a strong base or a strong nucleophile. So weak bases or weak nucleophiles, because they'll be attacking the carbonyl carbon, but not in a 1,2 manner. They will be attacking in a 1,4 addition. 1,4 addition. See, like these are all these different ones, like cyanide, like halides, like thiols, alcohols, amines. They are not like the organometallic. In organometallics, we have this exception of the organocuprate. The organocuprates won't give 1,2 addition. They will give 1,4. But all the other organometallics, they give 1,2. So here, after 1,2, we move on to 1,4, because that is our main aim. We are trying to see as to how this will facilitate the Michael reaction. So see, this is alpha beta unsaturated. All these are alpha beta unsaturated carbonyl, these substrate, electron withdrawing group, alpha beta unsaturated. So if we mark them 1, 2, 3, 4. Okay, 1, 2, 3, 4. So addition will take place here, because electron pair will be pulled here. So this will move over here between the carbonyl carbon and this, and therefore this fourth from this carbonyl carbon will get a positive charge, and this positive charge is not like the strong positive charge of the carbonyl, because in carbonyl, because this is generated by between two carbons, not an electronegativity difference. This is being generated by virtue of being present an alpha beta to an electron withdrawing. Here directly it is attached to electronegative. So this will be strongly carbon positive. But this will not be strongly carbon positive. This is soft or weak target. Similarly, these are also weak bases. So they won't be able to attack in a 1,2 manner. They'll attack in a 1,4 manner. on this softer target, that is the carbon double bond carbon. So we will get a 1,4 product. As you can see, in all these cases we are getting a product which is of the type 1,4. Now let's see here, organometallic. What are we getting here? 1,2, because, and this bond has been untouched because this is soft, whereas this, from the Grignard reagent, this alkyl group is highly strong, so it will attack directly on the carbonyl carbon. So this will be a 1,2 addition. As I have been saying, the exceptions are organocuprates, where we will get, in this case, this will attack the C2H5, this group will attack at which position? At the 4th position. So we will be getting a 1,4. Now this 1,4 addition is also called as the Michael addition or the Michael reaction. Now let's try to develop the strategies for it, because we've seen that what is being attacked, in which manner, where 1,2 is taking place with strong nucleophiles, where 1,4 is taking place with weaker bases or weak nucleophiles. They run parallel. Now let's see the synthetic strategy then, so as to design a synthesis using this Michael reaction. Now we have this is a carbonyl, and we know this is basically acetone in the presence of a base, because alpha position, so H positive given off, and this is carbon negative. And carbon negative, that is, but it's a strong base because it is not stabilized. You follow? We saw earlier, we will soon see that the ones which are attached to electron withdrawing groups, strongly electron withdrawing groups, they are stabilized, highly stabilized due to resonance. So this is not the case with this. This is a strong base, so it is a poor Michael donor. Weak bases are good Michael donors, whereas strong bases, we must understand, they do not represent, or they are very poor as far as Michael donors. They may be strong bases, but for them to qualify as Michael donors, we need them to be not strong but soft, weak, because they are attacking a soft target, carbon double bond carbon. They are not attacking carbon double bond oxygen. So this, in other words, if this is the type of reaction, that is, this is negative, and here what will happen? We have got this carbon double bond carbon to attack this and form this type of a product. This type of a product here, because this is negative, this will attack this, this will be pulled here. So as a consequence, this will become positive, because this is alpha beta unsaturated. So it will give us this product. But this is a poor Michael donor. So let's see if the same compound can be synthesized, this compound, this product, by using the proper method, that is a soft base, a weak base. Here is the reaction for the weak base. Now how is the reaction taking place? Again, instead of this double bond here, now we have got CH2 over here. Slightly modified it and increased the carbon here. That is, over here we have generated alpha beta unsaturation. And this extra, because this carbon here, see, this was CH2, this is added here. So carbon number remains the same, and naturally our product will also be the same. But the mechanism will be different. Now this time, this CH2, unlike this CH2, this is stabilized by these two carbonyls. This bond will move here. This will be the enolate. And in the second resonance structure, this will move here. So this will be the enolate. So, you know, they are doubly very well stabilized. So it is a good Michael donor. A weak base. Why a weak base? Because this is not available all the time. So it's a weak base. So this carbene ion here will now attack this alpha beta unsaturated, and as you can see, we are getting the same product as above, but in a better yield, more efficiently, a green approach using less drastic conditions, and hence this is the correct way or a correct strategy for Michael reaction. So remember, Michael reaction means that it is a greener approach, milder approach for the formation of the carbon-carbon bond, which is being formed here, but not such an efficient method because we'll have to use drastic measures because this is a strong base. Here this is a weak base. So this weak base will attack this soft target and we will get our product. This is the synthetic strategy, and while we are selecting a Michael reaction. Now as to how the mechanism proceeds. This is an alpha beta unsaturated carbonyl. This carbonyl, by this oxygen, which is electronegative, so it will pull electrons towards itself. Hence these electrons, pi electrons, alpha beta, will move towards the carbon because it's got a positive charge now, and therefore this position will get, the fourth position will get, this position will get the positive charge, okay, which we showed earlier, 1, 2, 3, 4, how 1, 4 addition takes place. And here this is the Michael acceptor, this 1, 2, 3, 4, okay. Now we can see that positive charge is generated in this in two positions. So at carbonyl carbon, because these electron pairs will be pulled up here towards the electronegative oxygen, and simultaneously also at this position when these electron pairs they move up here. Now the question is that the Michael donor, which is a carbene ion, can attack either of these. Where will this attack? Now Michael donor, as we know, is not strong. It is a weak base, a weak nucleophile. Therefore, it can't attack this position which requires a strong nucleophile. Hence, it will attack this fourth position so that we get the 1,4 product. Now, this is our Michael donor. Michael donor means two electronegative groups. This is the CH2 in between. This in the presence of a base, because it is CH2 in between two electron withdrawing. So they are withdrawing electrons from carbon, carbon in turn from the H's. So carbon-hydrogen bond becomes weak and can easily be pulled by a base OH negative in the form of H positive. And here we have our carbene ion, which is stabilized by these two carbonyl groups. So it is a weak nucleophile, a weak base. And this Michael donor will therefore attack the fourth position and not this strong carbon positive position. So Michael addition will take place now, in this manner, where we will get the product as the carbon negative, that is the carbene ion attacks this carbon positive. So a bond will be formed, a carbon-carbon bond, and therefore on acidic workup, what will happen? This electron pair will return here. This bond will take up an H positive from the acidic workup, and hence we will get this type of an enol, and this enol, so therefore this will form the more stable carbonyl, the enol. So therefore this will H positive from here, leaving the negative charge electron pair here. So this will move here, and this carbon electron pair will move here attached to the H positive. So we get as a result our Michael product. So this was the Michael reaction in the most simplified form and the basic. Let's see one or two problems related to this. Now this is a double alkylation. Double alkylation means, again, this is alpha beta unsaturated. Alpha beta unsaturated means it can easily be forming a carbon-carbon bond because this is a good, we can say, Michael acceptor. But what happens here if we try to form two bonds, that is double alkylation? How can these be formed? Because we know alkyl group can be introduced here at the fourth position, 1,4. But what about this place? So we use this capability of what? Of our 1,4 addition or the Michael addition which is given by what type of bonds, which is given by R. We can say which bonds? Organocuprate. So it is given by organocuprate. Here's the double bond. So this will therefore attack here at the 4th position. This will attack here at the 4th position, and we will get this product by virtue of see, we are using now organocuprates because we know organocuprates give 1,4, not 1,2 addition. It won't attach here. It will therefore attach here at the 4th position, 1, 2, 3, 4. So this will be the product that will be formed. And after this, the next strategy is not acidic workup. Had it been an acidic workup, then of course we would have formed an H over here with OH, and things would have been that this would have been the product with this forming this coming here and this forming H over here with the H positive. But no, that is not the case. Here, rather than the acidic workup, we are now using an alkyl halide. An alkyl halide, rather than an acidic workup, will give us, because this is CH3 positive. So when this bond returns here, this won't associate with H positive, rather it will associate itself with CH3 positive, and we get a double alkylated product. Why I have discussed it here? Because this is an application of Michael addition using this organolithium, and a variation in the second step, that instead of using an acidic workup, we are reacting with this alkyl halide. Now let's see one of these applications of Michael addition reaction. There are many more, but this was the simplest and the one which was tried long time back, very early. So application is the synthesis of warfarin. Now warfarin is an anticoagulant because to prevent blood clotting. So how does this work? See, this is a coumarin, this ring, together with this 6-membered ring with oxygen, the heteroatom. This is coumarin, 4-hydroxycoumarin. 4 hydroxycoumarin. Now when this reacts with benzyl acetone, and I'm sure you are able to make out a little benzyl acetone. So what will happen? Again, this Michael addition will take place, and we will get what? We will be getting our product as the anticoagulant, that is warfarin. So warfarin will be synthesized as a consequence of this reaction. So here we saw just one application of our Michael reaction. There are many more applications. We've just seen to one of them. Now when we are studying Michael addition, we cannot leave a Robinson annulation behind. Why I am doing a Robinson annulation here? Because earlier on in our name reactions, we have done aldol condensation. So this is a combination of the two, that is Michael addition and aldol condensation together give us a beautiful product that is a cyclic structure, and rings are important in many of our pharmaceutical compounds, pharmaceutical chemistry, and besides that in many natural products and bioactive molecules. Therefore this reaction, I thought I should take it up because it is dealing indirectly with Michael addition and together with Robinson annulation, together with aldol condensation, and we have now completed our Michael addition in this simplistic view, and the aldol condensation we have done earlier very much in detail. So combining the two, we are getting annulation, means ring formation or cyclization. Now how does this reaction go? Here, as we can see, is our mechanism for this. We will see to this after this. This is our initial starting, these two, that is here we have an active hydrogen over here, active methylene activated by this, and moreover we have this over here, that is the alpha beta unsaturated carbonyl compound. So what will happen is that in the presence of this, a combination will take place in such a way so that we get our cyclized product. The cyclization is occurring and we are getting our cyclized product. Let's see as to how this mechanism operates. Because this is the carbonyl that we have got here, and here we have got the other part, that is our activated compound. So in the presence of a base, what will happen? In the presence of a base, as I was mentioning, therefore a hydrogen H positive will be abstracted, so we get a carbanion. Now the Michael reaction will proceed. Once this carbanion has been generated, it will react with this alpha beta unsaturated, because this is a carbonyl electron withdrawing group. So with the result, now we have developed this negative, hence this will be what? Carbon positive, and this will react in such a way, because carbanion has been generated. So this is the carbanion over here. So alpha beta unsaturated, carbon carbon bond will be formed, because this will pull the electron towards itself. So this will bond will move here, and here is the positive charge. That is, one is the Michael donor, the carbanion, and one is the Michael acceptor, this positive. 1, 4. So what is the addition taking place? 1, 2, 3, 4. At this position, carbon negative with the carbon positive. So once this has been formed, that is a CH-CC bond has been formed, that is CH2, CH, CH, O negative, because those electrons have moved here. That's why the fourth carbon position, carbon has got a positive charge. This is the Michael reaction that we are looking to on CH3. Now what will happen in the presence of, again, the base? What will the base do? Because here this will move over here, so this H positive will add here, H positive, like the acidic workup, and so we will get this product. Now this product, as we can see now, CO, again what will happen in the presence of a base? Because we know now we are proceeding towards the aldol after this. That's why it's a combination of both the Michael as well as the aldol. Now this will react further, and we will see how cyclization will occur, because this CH3 has got acidic hydrogen. It is alpha to this carbonyl. So H positive will be pulled by the base. So we will get over here, H positive moves, leaving its electron pair. Enolate is generated. Enolate. So the conditions for aldol. So now this becomes, instead of CH3, it becomes CH2, and this is O negative. Now this will O negative, this electron pair will be pulled here, and since this is a carbonyl carbon, this carbonyl carbon electromeric shift, so this carbon will get a positive charge. When this gets a positive charge, now this bond moves back, so this is no longer required, this breaks, and here this adds to this. In other words, cyclization is now taking place by virtue of what? The aldol condensation. They are properly positioned, so cyclization takes place. And here, since this on this carbonyl carbon, this has been carbon negative, this was carbon positive. That is why this double bond pi electrons added here, nucleophilic addition. So now when this is O negative here, again the base, what will it do? It will now attack. So we will get OH. And in brief, you can say, though I've shown these here, you know what is the end product then once this aldol has been formed? That is elimination of H2O, and a double bond will be formed here. I've shown it just stepwise, that in the presence of a base, how this will abstract this hydrogen. So a double bond will be generated here. So this electron pair over will move back here, a double bond here. And when this double bond moves back, the electron pair moves here, OH will be eliminated. In nutshell, we can say that basically it is the elimination of alpha-beta elimination of water, elimination, H and OH. So this was the Robinson annihilation, which is a combination of our Michael addition and Michael addition, carbon negative here, and this is alpha beta unsaturated, so it gives a 1,4 addition, 1, 2, 3, 4 at this end. So this CH2 is added here to this carbon negative, and once this has been formed, then this is the mechanism as is shown here. Then what will happen in the presence of a base? First, we will get, like an acid workup, we will get a Michael product, but which has an activated CH3. So base is present. This CH3 will turn into H positive, will be eliminated from here, and once this is eliminated after the formation of the product, we will be now proceeding with the aldol condensation, because we will get at this end a CH2. This CH2, because this carbonyl is here, so electromeric shift carbon positive, so this bond here, pi electron adds to, it acts as the nucleophile, so it adds here. And how is it held? Because of this enolate. So now this enolate, this oxygen negative, this electron pair moves back, so this bond attaches here, carbon-carbon bond is formed, aldol condensation, and we get this O negative, this O negative with H positive again from the base, which in our case now this C2H5OH will give us the aldol, and this by elimination of water, alpha beta elimination, will lead to the formation of this cyclic ring or R product, that is the Robinson annihilation. Annihilation means ring formation. So I hope you have followed this reaction, the important Michael reaction leading to first formation. First, initially, we did how the mechanism, the simple mechanism. We did what a Michael donor is, what is a Michael acceptor. So what is a Michael donor? A Michael donor is that compound which is forming the carbene ion. That is, it is a methylene group situated in between two electron withdrawing groups. And what is a Michael acceptor? A Michael acceptor is an unsaturated compound which is attached alpha beta unsaturated to an electron withdrawing group, which can be carbonyl, which can be CN, as we have shown seen earlier, that we can get various variations of this Michael acceptors and Michael donors. And we saw as to what 1,2 addition is. The direct addition on carbonyl is the 1,2 addition, whereas the addition on alpha beta unsaturated carbonyls or alpha beta unsaturated compounds with an electron withdrawing group is known as a 1,4 addition, for which we do not require a strong base, but we require a soft or a weak base.